Sorry everyone. There was some issue with YouTube. So the live session crashed suddenly. So we can continue from the beginning. If you are here, please leave a hi in the chat so that we will know you are here. Okay. So hopefully most of you are here. So let me again start from the beginning of what I wanted to do today. Uh, so today's session, I said I am going to go complete however possible about cyclic groups and then move into the normal subgroups part. Now, so we took Zn, Z6. So it has 0, 1, 2, 3, 4, 5. And we consider the generators of Z6. So we know that for any n, the number of positive integers less than n and relatively prime to n will be the generators of Zn. So the generators of Z6 are 1 and 5 because among all the integers from 0 to 5, only 1 and 5 will have GCD 1. Hi Bijal, I think it is live now. Fine. So for Z6, we know that the generators are 1 and 5 because 1 and 5 are relatively prime to 6. Now we are creating a new group, new set, and we are defining a new operation from this. Now we are calling this as U of 6. U of 6 is the collection of all generators of Z6. Now we are going to show that this is going to form a group under multiplication modulo 6. That is, what do we mean by multiplication modulo 6 is, here this is addition modulo 6. That is, we add the positive integers and then divide it by 6 and take the remainder as our end product, end result. Now here what we do is, we are going to product the integers, product the positive integers, and then using multiplication modulo, using mod 6, we are going to read it and arrive back. Fine. Now we need to show that this forms a group. That is, this 1 comma 5 under multiplication modulo 6 will form a group. So we are not going to check each property because it has just 2 elements. So we go to the classic method of having our Cayley's table. So if we have Cayley's table, so that is, Cayley's table is a table where we try to write all possible operations between any 2 elements. Fine. So what we do is, this is multiplication modulo 6. We have only 2 elements, 1 and 5. So what we do is, we multiply those 2 elements and read it using mod 6. So 1 into 1 is 1. With respect to mod 6, it is 1. 1 into 5 is 5. With respect to mod 6, it is 5. 5 into 1 is 5. With respect to mod 6, it is 5. And 5 into 5 is 25. 5 into 5 is 25. So with respect to mod 6, we are going to get to be 1. Fine. Clearly, this table says that the closure axiom is true because however we multiply, The elements are again 1 and 5. Closure is true. Associativity, multiplication, since it is the usual multiplication, associativity is true. And you can clearly check the identity element to be 1. Because 1 into 1 is 1, 5 into 1 is 1. Also other way around. 1 into 1 is 1, 1 into 5 is 5. Sorry, 5 into 1 is 5. So the identity element is 1. And inverse of 1 is 1 and inverse of 5 is 5. Because 1 into 1 gives us 1. That is 1 multiplication modulus is something must give us 1 because 1 is the identity element. So it is nothing but 1. Same way 5 multiplication modulo 6 must give us 1. So it is nothing but 5. So all the properties are true and hence U of 6 forms a group under multiplication modulo 6. So from Z6 we constructed a new group. Not just, this is not a subgroup. Please be careful about the terminology. This is not the subgroup, but this is a new group. That is, we are defining a new set, having a new structure, and we are saying that this forms a group. And clearly, since multiplication is commutative, this is an abelian group. Fine. Now, so we will try to see how this u of n looks like for different n. Right? So u of 6 happen to be 1 comma 5 having just 2 elements. Now let us dig deep into other n, u of n for other n. So let us consider say z11. So maybe I will give a smaller number, say z7. So this is 0, 1, 2, 3, 4, 5, 6. So for Z7, we have 0, 1, 2, 3, 4, 5, 6. Now, what are the generators of Z7? What are the generators of Z7? Can you please leave it out in the chat? Generators of Z7. What are all the generators of Z7? So leave your answers out in the chat, please. Okay, Shebin. There is an answer from all numbers except 0 and 7. Shebin, please be careful with your answers. The set does not have 7 in it. So it has only 0, 1, 2, 3, 4, 5, 6. So except 0, every number is a generator because every number has GCD 1 with 7. So the generators of Z7 are 1, 2, 3, 4, 5, and 6. Now, so U of 7 will have 6 elements. 1, 2, 3, 4, 5, 6. So as I said, U of n will have all the generators of Zn. So U of 7 will have all the generators of Z7. So U of 7 under multiplication modulo 7 will form a group. You can check it using Kelly's table, but that is what we are not. That is not what we are going to do here. Now, under this multiplication modulo, please try to find order of each element. Please be clear with the question. I said with respect to multiplication modulo 7, this will definitely form a group. And now please try to find what will be the order of each element in this group. Please be careful. I again repeat, the reason is 1, 2, 3, 4, 5, 6 will have its own orders in Z7. But now we have defined entirely a new set and entirely a new structure on this set. So the order will be definitely different, may or may not be, but here it will be definitely different. So please try to find what will be the order of these elements here in U of 7. U of 7 under multiplication modulo 7. Try to find what is the order of each element. Clearly, 1 is the identity element here. So identity element order 1. So try to find the orders of rest of the elements. So please go one by one. What is the order of 2 here in multiplication modulo 7? Please be careful. Here it is multiplication. So 2 into 2 is 4 and 4 into 2 is 8. So it goes on like that. So here 2 power n is 2 into the usual multiplication. So order of 2 is 3. Yes, yes, Karparam. Order of 2 is 3. Because 2 into 2 4. 2 into 2 is 4 into 2 8. When we read with modulo 7, it is going to be 1. So order of 2 is 3. Now order of 3. What is order of 3? So it'd be a bit, you will be doing the process of calculating the order in a tedious way, I guess. So that is why it takes time now. So order of 3 can be calculated trivially, easily, if you have a multiplication modulo specified. Shebin says order of 3 is 4. No, definitely 4 cannot be order of any element here. The reason is the order of this group is 6 and 4 does not divide 6. So orders has to be either 1, 2, 3 or 6. So okay. So order of 3 is 6. Then order of 4. Maybe I think I can work it out once and show it to you for Z7 maybe. Sorry, U7 maybe. So order of 4 is 3. Okay. Very fine. So maybe let me calculate it and show it to you in an easier way so that it will be will not take so much time. So maybe I will erase this. I will have this here. So this is this is bit, then the process I'm going to do is just because we have multiplication modulo 7, it will be easy to calculate hereafter. So 1, obviously it is 1. So 2 into 2, 2 when with respect to multiplication modulo 7, it is again 2. So 2 power 2 is 4. Mod 7, we can't do anything. So 2 power 3 is 4 into 2, 8. Mod 7, 1. So order of 2 is 3. Fine. Now, everyone had an issue with 3. So we will do 3. So it took some time for you to calculate order of 3. Now, 3 square is 9. Modulo 7 will be 2 mod 7. Fine. Now, 3 cube is going to be 9 into 3 mod 7, which is same as 2 into 3 mod 7. That is 6 mod 7. Fine. Now, 3 power 4 is going to be, so clearly it is not 1. So now next, so 3 power 4 is going to be 6 into 3 mod 7, which is 18 mod 7, which is 4 mod 7. 3 power 5 is 4 into 3 mod 7, 12 mod 7, 5 mod 7, 7, which is 1 mod 7. So everyone would have calculated sorry for the trouble in between. Now everyone would have calculated this by calculating the entire thing. That is, you would have calculated till 3 power 3. Some of you might have calculated it till 3 power 3, 3 power 4, 3 power 5, etc. So you can always reduce it to mod in the subsequent steps, so that your calculation process will be a bit more easier. Fine. So order of 1 is 1, order of 2 is 3, order of 3 is 6, order of 4 is 3, order of 5 is 6. Okay. And order of 6 is 2. Yes. Okay, fine. Now, our next guess. Please look here. U of 7 had 1, 2, 3, 4, 5, 6. It had just 6 elements. And yesterday we had a fact that if whenever a group is of order n and it has an element of order n, then the group is going to be cyclic. So since U of 7, 1, 2, 3, 4, 5, 6 has an element of order 6, implies U of 7 is cyclic. Am I clear? So U of 7 is cyclic, but already we saw whenever we have a group to be cyclic, and if it is of order n, it must be isomorphic to Zn. So can you please tell what U of 7 is isomorphic to? So yesterday we saw whenever a group is cyclic and it is of order n, then the group will be isomorphic to Zn. Now here U of 7 is cyclic, and hence it will be isomorphic to. So there is an answer by Karpadam. She says it is Z6. So won't it be, there is a usual confusion which arises here. U of 7, so it may be isomorphic, it is cyclic. So our obvious thinking goes to 7 as Z7, but it is not true. So this is isomorphic to Z6. Okay, now there is a question from Mahesh. So he says U of n is not cyclic when n is not prime. Is it abelian? So we can always say that we cannot conclude the first statement what you said always. So let us see an example where it is going to fail. Okay. So what he says is whenever n is not prime, U of n will not be cyclic. U of n is not cyclic. So let us see where it fails and let us see what happens. Now, maybe I will leave it to you for do now, for calculating it now. Consider Z9. Z9 will have 0, 1, 2, 3, 4, 5, 6, 7, 8. Now, find U of 9. U of 9 will have 1, 2, 4, 5, 7, 8. I think I am right. So U of 9 will have these many elements. U of 9 will have 1, 2, 4, 5, 7, 8. I think I'm clear now. So now try to find order of every element with respect to multiplication modulo 9. Order of each element in multiplication modulo 9. Order of 1 is 1. So try to find order of 2, order of 3, order of 4, order of 5, order of 6, order of 7, order of 8, order of just a order till order of order of 1, order of 2, order of 4, order of 5, order of 7, order of 8. So only these elements you need to find the order. Now try to calculate the orders of the elements here, please, and list it down in the chat. So can you please tell me what will be the order of each element here? Order of 2, 4, 5, 7, 8. Order of 2 is, so it happens to be 6. Okay, fine. 2, 4, 8, 16. 22. Yes. Order of 2 is 6. Order of 4 is Order of 4 is 3. Fine. Yes. Order of 5 is order of 5 is so order of 5 is 6. Okay, fine. Order of 7. So I think order of 7 is also 6. No, 3. Is it so? 7 sevens are 49. With respect to mod 9, it is going to be 4. 4 sevens are 28. With respect to mod 9, it is 1. Yes, yes. Order of 7 is 3. And order of 8 is order of 8 is 2. 2? Yes, it is. Now, please look here. Here n is not cyclic. Sorry, n is not prime. But still, this group has an element of order 6. We have 2 elements of order 6 here. And hence, U of 9 is isomorphic to Z6. Fine. Now also we saw U of 7 is also isomorphic to Z6. So we can conclude that U of 7 is isomorphic to U of 9. So here U of n does not act like Zn. So they are structurally different. Also they behave so differently. So U of 5 and so there are few groups which need not be cyclic also. U of n. So let us look at one such example and then we will wind up with cyclic groups for today. So then we will move into normal subgroups. So you will see one example where this U of n is not cyclic and then we will move into normal subgroups. So hopefully it is clear till now. Please don't hesitate to leave out your clarifications in the chat. So I think we can find for Z8. So Z8 will have 0, 1, 2, 3, 4, 5, 6, 7. Now U of 8 will have 1, 3, 5, 7. So these are all the numbers relatively prime to 8. Clearly this is going to form a group, an abelian group. We are going to check whether this is cyclic or not. Now find the order of 1, order of 3, order of 5, order of 7. This is 1 obviously. So try to find order of 3, 5 and 7. Order of 3 is 2. Cross 3 into 3, 9. When we read with mod 8, it is going to be 1. 5 into 5 is 25. When we read with mod 8, it is going to be 1. So order is 2. Order of 7. Again, good answers, friends. Now, if you look at here carefully, it is a group of order 4. For it to be cyclic, it must have at least one element of order 4. So please recall, we said order of A is equal to order of subgroup generated by A. If suppose this happens to be cyclic, then we must have one such element A, where this must be equal to U of 8. Fine. That is, order of A, subgroup generated by A, must be 4. Fine. So you must find an element A in U of 8 such that whose order is 4. Only then we will have a generator for U of 8. But here all the non-ident elements have order 2. So there does not exist an element whose order is 4, and hence this U of 8 is not cyclic. It is abelian but not cyclic. We can give this as an example for a non-cyclic abelian group. So whenever we are in search of abelian groups which are non-cyclic, the examples are very less. We always move in with go with the examples for abelian groups as Zn. So this is one example where the group is abelian but it is not cyclic. Fine. So there is an observation from Mahesh. Another example of cyclic group U of n where n equal to PQ, P and Q are distinct primes. Okay, Mahesh. So I am not sure about this result, whether it is true or not. So I'm not sure. Maybe I need to confirm it later. If P and Q are distinct primes, if n is equal to PQ, then U of n will be cyclic. So I'm not sure about this result, so I cannot confirm it now. Maybe I will check it and clarify it with you later. Okay, so I think so our observations today were entirely about U of n. U of n in general need not be cyclic. It may or may not be cyclic. So in some cases it may be cyclic, in some cases it may not be cyclic. There is a general format of how U of n will look like, but I am not going to give you that now because we are not yet done with the direct products. It is related to direct products. So I think I will wind up cyclic groups here and move into normal subgroups of a given group. Okay. So I think if there is any clarification regarding this, please clarify it in the chat. If you have any clarification in cyclic groups, please clarify it in the chat now, because we will move on to cyclic groups now. Okay. So actually Mahesh was asking a question. Fine. So I'm not sure about it. I think it need not be cyclic in general. Whenever P and Q are two distinct primes. Maybe I need to check it and clarify it with you later. I will soon clarify you, Mahesh. Okay, so is there any clarification? I will wait for 2 minutes maybe. If you have any clarifications, please mention it in the chat now for cyclic groups so that we will move into normal subgroups. Okay, Mahesh, I think please check with 15 for the number of 15. So I think for 15 it is not going to, it may not work, my guess. So maybe you can try, or we will discuss it in the Telegram. Okay, so let me move into normal subgroups now. Fine. Okay. So also before moving into normal subgroup, I am going to give you few facts which are very much helpful in uh, exam point of view, CSAR net. So this will always help us. Please note it down always. If order of G is equal to P, where P is a prime number, then G is cyclic. So whenever a group is of prime order, it is going to be cyclic. Please be careful with the notation. I said just prime. So whenever we have any group of order a prime number, it is definitely going to be cyclic. Next, PQ, where P less than Q, P comma Q are distinct primes, and P does not divide Q minus 1, then G is cyclic. Okay. So these are some important facts. This is very easy to prove actually. This is very basic group theory, but need some sort of silo theorem to, where P is okay. So I think there was a sudden technical lag in between, sudden pause in between. Now let me repeat it again. So whenever we have any group of order prime, say 2, 3, 5, 7, 11, 13, etc. So every group of these orders are cyclic for sure. And also we saw another fact that any group G which is cyclic of order n is isomorphic to Zn. So whenever we have such a group, these are nothing but isomorphic to Z2, Z3, Z5, Z7 and so on. So whenever you are given any cyclic group of prime order, you can just consider it to be ZP. As simple as that. Right? Now, for the next one, please consider G to be a group whose order is say 15. So here I can write 15 as 3 into 5. P and Q both are distinct primes and P is less than Q. If here 3 does not divide 4 clearly, then G will be cyclic here. That is any group of order PQ where P is less than Q, P does not divide Q minus 1, G is going to be cyclic. That is any group of order 15 is cyclic. So in such a way, if any number exists of this sort, this satisfying these properties, those groups are cyclic. Fine. So these two are very important facts which we are going to repeatedly use in exams. So let us move into normal subgroups. So in the first class, we discussed what is a subgroup of a given group. So we know what is a subgroup. So what is the need of such normal subgroups? Fine. Now, so the need arises, we can say that the need arises either from homomorphisms or mostly in homomorphisms, or when we defined cosets, there was a curiosity to know, to check something. So we will define cosets, and before that, I will try to give a motivation where this is now. Why this is necessary? Consider two groups, say some G1 to G2. If suppose we have a homomorphism in between. Now, in general, this homomorphism need not be 1 1. Fine. Now, there is a property of homomorphism. Okay. I think I have not defined what is kernel. So fine. Let me try to define what is normal subgroup here. Why do we need normal subgroup directly? Now, in general, the mapping, the homomorphism need not be 1 1. So what we are trying to do is, we are trying to split up this set into something where now this is not a mapping from G1 to G2. Now we are considering a different set where all the elements here will be considered as one set. All the elements here will be all the elements here will be considered as one set, and this will have collection of these sets. So hopefully I am clear. So what we do is, we have G1. We are splitting up this set into some kind of partition where this entire set will be considered as one single element. This entire set will be considered as one single element. This entire set will be considered as one single element. This entire set will be considered as one single element. This will be considered as one single element. Likewise and likewise. Now, if we are going to partition it in such a way that after considering this set as one single element, this mapping becomes 1 1. So our aim is to break the set into different subsets and consider it as a single element, and then try to convert the mapping as a 1 1 map. A given homomorphism into 1 1 map. So what our ultimate aim in defining normal subgroups. Sorry. So how we are going to do this? To do this, we need normal subgroups, and we will try to go in deep into what is normal subgroup. Now, before defining normal subgroups, we are going to define something called cosets. So we will define. Okay, I think I'm back live now. Is it paused or it is back live now? Okay, fine. Now, we will define what is meant by a coset. Now, let G be a group and H subgroup of G. Now, take an element in G. We define the left coset to be AH. So by the literal meaning, coset is going to be one set where we denote it by AH. We are going to call it left coset of H because it depends upon the set H. Now AH is defined to be set of all AH such that H varies over H. Now, that is, by left coset of a subgroup H, we mean the set of all AH where H varies in H. That is, fix a try to left multiply A to every element of H, we will end up with a set, and that set will be called the left coset of H. Fine. So this refers to the operation given in the original group. Now similarly we define right coset of H as HA equal to set of all HA where H varies in H. That is, we are going to multiply A to the right of every element of H. As simple as that. This may be simple, and our intuitive idea is these two might be the same or might not be the same. So we will see a few examples where this is the same and few examples where this is not the same. We will try to list down the elements in the coset, and we will try to find what happens. Okay. So we are fixing an element of the group, so you can find coset for every element in the group. Okay. Now, consider Z say Z6 under addition modulo 6. Fine. Let us consider the subgroup generated by 3. So subgroup generated by 3 will have 0 and 3. Now let me denote this by H. So here it is addition modulo 6. So 0 addition modulo 6 H is going to be, we are going to add 0 to each element here. So this is going to be 0 plus 0 is 0, 0 plus 3 is 3. Fine. Now, 1 addition 6 H, that is, this is a coset. This is the left coset of H. Fine. So this is going to be, we are going to add 1 to every element of H towards the left. So 0 plus 1 is 1. Sorry, 1 plus 0 is 1 and 1 plus 3 is 4. I am careful with my words because multiplying it, operating it to the left and operating it to the right might be totally different. Fine, might be. So we don't have any examples for by to show that, but still we will proceed. 2 addition modulo 6 H is going to be, say what? 2 and 3 addition modulo 6 H is going to be 3 and 0. Because 3 plus 0 is 3, 3 plus 3 is 6. When we read with addition modulo 6, it's going to be 0. So maybe we can proceed on with 4 addition modulo 6 H and 5 addition modulo 6 H. Fine. So this will result in 4 plus 0, 4, and 4 plus 3 is 7. 7 addition modulo 6 is 7 in mod 6 is 1. And this is going to be 5 comma. Now, if you look at the observations carefully, these cosets behave in some particular way. That is, if we had taken a subgroup having 2 elements, and clearly every coset has exactly 2 elements. Number 1. And number 2. Every coset has the same elements, and here what happens is the left coset, and if you try to find what is the right coset, it happens to be the same because this is an abelian group. So adding it to the left or adding it to the right doesn't matter. Right? So if you look at it carefully, every coset has exactly the same number of elements as H, and here in Z6, your left coset happens to be the same with the right coset. Fine. Now, one more thing. If you look at carefully, if you look one other thing carefully, 0 plus h is the same subgroup. 3 plus h is the same subgroup. If you take an element which is not in the subgroup, so there are 4 other elements which is not in the subgroup, 1, 2, 4 and 5. When you try to find the coset corresponding to it, it happens to be a different set than the subgroup. But if suppose the element with which you find the coset happens to be in the subgroup itself, the coset you get happens to be the subgroup itself. So hopefully what I am trying to say is clear. The first fact is the coset has exactly the same number of elements as the subgroup. Number two is the subgroup. If suppose the element is in the subgroup, the coset appears to be the same, and if the element is not in the subgroup, the coset happens to be something different. Fine. So we are going to try and infer it in general. So before trying to do that, we will see one another example of finding a normal subgroup. So now this is a normal subgroup of Z6. Clear? Because 0 plus h is same as 1 plus h. Okay, I haven't defined a normal subgroup yet. Sorry for that. So we will define what is a coset. We will try to find what is a coset. Fine. Consider Z under addition. Now we will consider one subgroup of it, say 2Z. Now, because this has infinite number of elements, it is not humanly possible to check everything, but we will try finding out what happens to every coset. So let this be my h. So what is 0 plus 2z? 1 plus 2z, 2 plus 2z, 3 plus 2z, and so on. These are going to be subsets of z, and can you please check out what is going to be 0 plus 2z, 1 plus 2z, etc. Can you please list out the elements? So I think I will wind up with this coset example, because I think it is exceeding the time. So maybe I will define what is normal subgroup in the next class whenever possible. I am not sure when is the next class on normal subgroups will be. So whenever the next class is, I will define what is normal subgroups and we will move on. So I will wind up with finding these cosets for today. Now, can you please check what is 0 plus 2z, 1 plus 2z, etc. and leave the answer in the chat. Okay, Karparam, good observation. Any even integer a in z, a plus 2z is 2z again. So we recently observed something. Good observation, Karparam. So we recently observed something. If the element happens to be in the subgroup itself, then we get the subgroup itself as the coset. So this is going to be 2z, 2z, and so on for every even integer. So for the odd integer, it is going to be nothing but the set of all odd numbers. and you can verify it. It is going to be plus or minus 1, plus or minus 3, plus or minus 5, and so on. So this is going to be the left cosets. So there are only two left cosets here if you look at it carefully. So they are nothing but 2z and plus or minus 1, plus or minus 3, etc. So if you look at the right cosets also, they are going to be the same. So please try to check, find the cosets of different groups we have experienced till now. Find, take any subgroup of the given group and try to find the left coset and try to find what happens to its right coset. I think I will wind up for today because it has been a very long session now. So I will continue with defining normal subgroups in the next class, and then we will proceed on to quotient groups. So to define quotient, we need normal subgroups. So we will proceed on with quotient groups in the later class. So I think the session was useful. Please leave your comments in the chat, and we can have discussion in the Telegram group. If you have any clarifications, please don't hesitate to ask your doubts or clarifications. Please stay safe, and thank you. If you have clarifications, please mention it in the Telegram group. Thank you.